Hey guys, we are continuing on Unit 5. Today we're talking about nuclear equations. So a little bit about radiation and just different nuclear reactions and stuff like that. So your question of the day: why is it important to understand why certain atoms give off radiation or radioactivity? What practical purposes does this serve in society? So I'm going to give you just a second. If you need to pause the video, go ahead and pause it, and you can write down your answers in your notes. Okay, so I would have written something kind of like this. Understanding why certain atoms emit radiation is going to be really crucial to society or in society, whether it be for carbon dating substances or using radioactive isotopes for medical procedures, or maybe generating energy from uranium or plutonium or anything like that. Knowing why atoms give off radiation and that type of radiation allows us to select certain isotopes of radioactivity based on whatever our needs are. So write something like that down in your notes. Okay, so let's review a little bit. After element 82, which is lead, there's too many protons in the nucleus, so no number of neutrons can hold the protons because they have a strong nuclear force. The repulsive force of the protons overcomes the attractive nature of the neutron's strong nuclear force. The nucleus is too large. It begins to emit particles in order to reduce its atomic mass. Okay, so that's going to be called radiation or radioactivity. Most atoms normally have more neutrons than protons so that the proton repulsion is kind of contained and there's not just protons kind of shooting off. So any atom after lead is constantly giving off radiation to relieve that overcrowded nucleus. What type of radiation can a nucleus emit in order to reduce its atomic mass or in order to achieve 82 protons? So this is when Ernest Rutherford comes in. He deduced these three types of radiation in 1899 by conducting a few experiments. So here's kind of a picture of that. We have alpha radiation, we have gamma, which is more of just energy or pure light, and we have beta radiation. So alpha radiation at the top is 2 protons and 2 neutrons, which is just a helium nuclei. And at the bottom, beta is just an electron. Neutrons in the nucleus use strong nuclear force to pull protons together. Here's a chart to kind of summarize Rutherford's findings. Alpha is going to be really slow, little energy, and then we have gamma all the way at the bottom, which is no mass, but it's the speed of light. It's going to be dangerous depending on what the type of light wave it is. Elements can be radioactive though, even when they're not above atomic number 82. Give me just a second.
And Angela Rivera to please come to the office. Kate Ross and Angela Rivera, please come to the office.
Okay, sorry about that. When looking at what is known the zone of stability, we find that each element in nature has an optimum or stable ratio of protons to neutrons. Elements that contain more or less neutrons than the average for that particular element will undergo radiation so that they can reach the optimum ratio of protons to neutrons. So there are other types of radiation. Most zinc atoms usually weigh 65. The zinc atom is likely to be radioactive because it has less neutrons than the average. So our first type of radioactive decay or first type of radiation is alpha production. Here's an example of what that looks like. Again, the helium nuclei, you can replace that just with alpha. It means the same thing. So this occurs with elements over 82 with too many protons and neutrons. Next we have beta radiation. Beta is just going to be an electron. So at the very right side, you could also replace that with the beta symbol if you wanted to. Converts a neutron in the nucleus into a proton and an electron. The electron's going to be ejected. The atomic number of the atom increases by 1. So that's what happens here. My atomic number is the bottom number. On the left, it's 90. On the right, where it says PA, that's 91. So it increased by 1. usually occurs with atoms that have an excess of neutrons in nature. This reduces the number of neutrons and increases the number of protons, but not to a 1-to-1 ratio, only to a manageable ratio within the zone of stability, where neutrons can still stabilize protons within that strong nuclear force. Next, I have gamma production or gamma ray. This can be super hazardous, as you know. Gamma is written there on the far right side with that gamma symbol. Another type that we haven't really talked about before is called positron production. So a positron is where it says E with a 0 on the top and a 1 on the bottom. It usually occurs with atoms that have a deficiency of neutrons for a given number of protons in nature. It converts a proton into a neutron and into a positron. Usually emits gamma radiation as well, but since gamma radiation has no mass or charge, it is optional whether or not you need to write it. Then we have electron capture. That is what this looks like here, where I have kind of that electron on the left, and then on the right I have gamma radiation. Okay, now we have nuclear transmutations. Scientists have been able to convert one nucleus into another by bombarding nuclei with various particles. This is very rare. It's going to be difficult to convert one element into another. Here's an example of the first transmutation performed by Ernest Rutherford in 1919. He transformed nitrogen into oxygen by bombarding it with an alpha particle. So here's the reaction. I have nitrogen plus alpha particle, which is the helium nuclei. When that happens, I now have oxygen, and then I have a hydrogen. Here's a couple more examples. You can write those down on your notes if you'd like, and we're not really gonna talk anymore about those. We can also use shorthand notation for these. So in the red box at the bottom, my target nucleus is going to be written first with the mass number and with the atomic number. And then I have the bombarding particle, so was it alpha, beta, gamma? And then I have the ejected particle, so usually a proton. And then I have the product nucleus at the end. What did it change into? Next, we are talking about nuclear fission and fusion. Fusion is combining two light nuclei to form one heavier, more stable nucleus. So that's written out here. Fission is splitting a heavy nucleus into two nuclei with smaller mass numbers. Possible with certain types of isotopes of uranium and of plutonium. Okay, the sun creates its energy by fusing hydrogen atoms into helium. Scientists during World War II deduced how to split uranium and plutonium atoms to create larger amounts of energy. This is done in nuclear bombs and in reactors. Okay, so now we can practice. We can determine various parts of a nuclear reaction using algebra. The numbers on the top represent the number of protons for a particular atom or particle. So these are the ones on number 12 on your notes that you need to go ahead and fill in, and we'll answer them as well. Okay, the numbers on the top represent the mass. Remember, only protons and neutrons have mass. So on the top, my mass number, I have 232 and I have 228. So what's on the left side has to be equal to what's on the right side. So I would do 228 and add whatever number I need to add to get to 232. You can do the same thing on the bottom. I'm trying to get them to equal on both sides of the arrow. So on the left I have 90, on the right I have 88. I need to add at least 2 to get to that 90. Okay, the bottom numbers on the right side should total to 90. The top numbers on the right side should total to 232. Here is what that looks like on the bottom. So that's a helium nuclei, which means if that's a helium nuclei, this is alpha radiation. You can insert the HE with the numbers, or you can just put an alpha sign, whichever way is perfectly fine. You don't have to show its charge, but remember that these particles have a +2 charge. Here's another practice problem that you'll need to write down. Your thyroid glands absorb nearly all the iodine in your body. When radioactive iodine, also known as I-131, is taken into the body in liquid or capsule form, it concentrates in thyroid cells. The radiation can destroy the thyroid gland and any other thyroid cells, including cancer cells, that take up iodine, with little effect on the rest of your body. So this can be kind of confusing. I have my iodine, and then I have beta, or breaks down and has beta radiation. So in order to make the algebra work, chemists go ahead and put a -1 on the beta particle. Technically it has a -1 charge. It's not a proton, but we really just write it this way so that the algebra works out. Notice the number on top of the beta particle is a 0 because a beta particle is just an electron. It doesn't really have a mass. You can also just write E- instead of the beta symbol if you'd like to. So again, that equation at the top, I need both sides to equal, which means I need 131 on the top of both sides. I need 53 on the bottom of both sides. Yep, let's see. So again, this is beta radiation. I would need to fill in xenon, which is what I did over there. 131 on the top, 54 on the bottom. If you do algebra, both sides equal. So like on the bottom, xenon is 54, but then beta is -1. So 54 minus 1 is 53, which means both sides are going to equal. Okay, here's a shorthand practice problem. We can go ahead and figure out the target nucleus, which is whatever the radiation is not. So helium is an alpha radiation, so we're going to look at the aluminum. That's my target nucleus. My alpha particle, or my bombarding particle is going to be the alpha, which is the helium. Ejected particle is going to be this neutron, and the product nucleus is whatever element you have left over, so it's going to be phosphorus. Okay, let me write that out for you so it makes a little more sense too as we go here. Okay. So on this last one, my shorthand practice, I have, let's see, my target nucleus, which is just Al2713. In parentheses, I have my bombarding particle, which is that alpha particle. It's supposed to be an alpha. Ejected particle is whatever it gave off. It gave off a neutron, so I can just write it N. And then my product nucleus, oh no, was that phosphorus. So this would be that shorthand notation for that problem. Okay. So you have a little bit of guided practice problems. After that, you have a worksheet that should be a lot of review from last year. So as always, please let me know if you have questions.